Okay, let's see how you did on your chi-squared goodness of fit problems. So remember, we don't need our parameter, otherwise you'd be defining all the different proportions. So our null hypothesis is that the die is fair. Oh, look, I just said the is fair. The die is fair. And what I mean by that is that each face's probability is 1/6. And so alternatively, the die is not fair, so it's not 1/6. Now, let's go ahead and talk about the conditions random, that the die rolls are random. Now, it's weird on this independent. So if you think it feels strange to say 60 is less than 10% of all possible rolls, I mean, and I think that is kind of weird because anytime you have an infinite population, that's kind of an awkward thing to say. So what are we really saying here whenever we're talking independence about a die roll? Well, that each die roll is independent of the other die rolls. I mean, that's really what is more natural. So don't just blatantly go through all the motions. Think about what those conditions are saying. All right, so our large enough, remember we had to say all expected counts are greater than or equal to 5. And so since this is implying that all of the proportions are 1/6, then that would be 60 times 1/6. So all those expected counts were 10. So I showed that. And so the chi-squared model applies. And so we're going to, the name of this is a chi-squared goodness of fit. I went and I put my observed in L1, my expected in L2, and you have to manually put in the degrees of freedom, which is categories 6 minus 1, so 5. And so then this is what the calculator gave me. I definitely have a p-value greater than alpha, so I do not have evidence that the die is unfair and doing something other than expected. Here was another problem about the offspring. So here the null hypothesis is that the bodies in the wing types are distributed as genetic theory predicts, or as the genetic model, predicted by the genetic model. So something along those lines. And then of course, alternatively, we want to see if it's not. Okay, so we'll start off saying, yeah, it's as you say, but unless I find evidence otherwise. So we're assuming those 100 fruit flies are randomly selected, and I would imagine they're less than 10% of all such fruit flies. So here was my expected counts. So remember that there were a total of 16 parts when you had this distribution. So that means the first one was 9/16, and the second one is 3/16, and the third one's rate is 3/16, and the last one's rate is 1/16. So those were the rates that we were talking about here. And the goodness of fit, chi-squared goodness of fit. There we have our p-value, which is greater than alpha. So there is not evidence that the bodies and wing types of all such fruit flies are different from genetic theory. All right, this is an interesting one, and we really haven't talked about this a ton. So it's kind of something interesting I threw at you here. So we're talking about the distribution of the types of nuts. So they are claiming these rates, these counts of 20% cashews and 20% almonds. So they're claiming the counts of the nuts that are in there, not the weights of the nuts. So the weights is a quantitative variable, not a categorical. So remember that we have to have counts of how many nuts were in each category. So the way you could, so therefore chi-squared is not even an appropriate test because this is multiple quantities or multiple averages. So to change this, you could just open it up and then count how many nuts those were, the proportion of the nuts instead of the weights of the nuts. All right, here we go with some multiple choices. So I will tell you that on the problem I got this from, this right here was not on the original problem. So all it said was the information here about how it's normally distributed. So I gave you this picture to kind of give you a big old hint that with the normal model, then these are the percentages that are expected. The 16 and the 34 and the 34 and the 16. So that was the big deal that actually had made this problem difficult without that information. So when we do that, we've got our observed minus expected, quantity squared divided by expected, and of course we're summing those up. Alrighty then, next. So here we had the claims of the dog bites, and so they were wondering if it changes, if it's different for the different phases of the moon. So that means that if I add all of these up, I can tell that they had 144 pieces of data. And so if all the different moon phases had the same rate of dog bites, then there would be 36 in each quarter. Okay, so they would be the same rate, a fourth. So, first of all, this doesn't prove anything because this is an observational study, not an experiment. And so then when I went and read or did the chi-squared goodness of fit, it gave me a p-value that was greater than alpha, so I don't reject the null. So I do not, these do not give me enough evidence to reject that the dog bites are happening at the same rate regardless of the phase of the moon. Okay. All right, and then here's another theory about the blood types, and then we were given the percentage rates for those blood types. And so when I put in my information, you can see I put in my observed. My expected was 2 out of 200. So I did the percent times the number in my sample. So here is how I computed those expected values. And I could have computed them right into my calculator there. So 0.025 is the p-value. So that means, so it's significant. If your p-value is less than alpha, it's significant at that level. So I have evidence at the 5% significant level. So my p-value, my data is significant at the 5% level, but not at the 1% level because 0.025 is not less than 1%. Okay? And so then here was another one of those ratio problems. I wish I would give you something else other than the 1 to 3 to 3 to 9 because I'm going to have students think, oh, it's always out of 16. Well, if you get a different set of theoretical claims, it could be out of a different total. So keep that in mind. So there we go. We had a p-value that was less than alpha. It barely gave us evidence that the distribution is different. Okay. Then here's our AP tester trio. So let's take a look at this. You had to remember quartiles and median and all that kind of stuff. So the one that's true is A. Now I remember when I first did this problem, I wondered how can they say at least half and or less than or equal to 44 and at least half. Well, if you had a whole bunch of pieces of data that were 44 or several pieces of data that were 44.27, then you could have had all of these ones above it and then all of the ones below it, okay? But if you had several of these, then you actually could have kind of been a little bit into the other quartile. So you could have at least half, a little more than half. All right, and I put the reasons why no on the other, that the other ones were not correct. Remembering that quartiles are 25% in those sections. So on this problem, we use these summary statistics and we did the IQR rules. So, and then I did the standard deviation rules. So let's remember those. So for the upper fence, Q3 plus 1.5 IQRs. And the lower fence, Q1 minus 1.5 IQRs. Remembering that the IQR is Q3 minus Q1. Now, once you have defined that fence, so upper fence at 159. So if you think about, here is our data, and here here's our fence. Okay, so let's say that's our fence at 159.5. If the maximum is above the upper fence, then you have an outlier. And then here is, say, this is the lower fence at 95.5, but look, the minimum is 96. So it's inside the fence. It is not below the lower fence. So to be an outlier, you have to be above the upper fence or below the lower fence. Above the upper fence or below the lower fence to be an outlier. So whether you did the standard deviation rule, which I have that computed here, or the IQR rule, you had just one, or at least one upper outlier. The only way to have at least two is if you knew there was at least one upper and at least one lower. Okay? All right, now this is a cumulative frequency graph. So that means that, we could figure out IQR and all that kind of stuff easy. So remember that this is the 30th percent. So I could have done like, here's the 25th percentile, and here's the median at the 50th percentile. This has got the 75th about right there. Anyway, so see, you could remember all the stuff you could do with this. You could make a box, and then you could compute what the IQR is, and you could figure out what a fence is and if you have outliers. But they just asked you to interpret the point 30.6. So they ask you to interpret this point here. So remember that the x-axis is the sugar content and the y-axis is the cumulative frequency. So that's telling me that 60% of the drinks have 30 grams of sugar or less. So it's this percent of the Y's have this amount of X or less because of the cumulative nature of a cumulative relative frequency graph. Okay, that's it for the first part of our AP Tester Trio. All right, then, hope that worked out for you, and I will see you in the next set of notes.